So let's take a look at the normal force. So a force is a push or a pull, and the normal force is something that's a little bit different and a little bit confusing for some people. So officially the normal force is defined as a supportive force. So whenever you put your hand on something or if you're pushing on a surface, what you're actually feeling is that normal force. So really all it's doing is supporting an object. And I like to call it kind of a lazy force because it only pushes as hard as necessary. So one other thing that tends to get people is they think that every time you put something down, you get a normal force. Every time you're resting, if you're leaning up against a wall, you feel a normal force. So a lot of people think that the normal force gets its name from the fact that it's kind of always there. It's normally there. It's that kind of idea there. But normal is actually a mathematical term. Normal is defined as something that's perpendicular. So anytime you're drawing a normal force, you can always guarantee that it's going to be perpendicular to the surface. So if you've got a table with a box resting on it, well, the force of gravity is pulling it down, and this force that is preventing this object from just straight falling is that normal force, and it's perpendicular to that surface. So if you've got something on an incline, say, then you've got gravity pulling it straight down, and the reason that the object's not just falling straight down is because there's a normal force. And as I said, it's always going to be perpendicular. So in this case, that normal force is going to push off to the side. And what might be confusing for people is they think, well, how is that perpendicular? Well, if you rotate your head, and in this case I'm just going to rotate the object here, that normal force is perpendicular to the surface. No matter how steep that incline is, or no matter how or what's going on with it, it's always going to be perpendicular to the surface. Now obviously, if you turn that surface straight 90 degrees, then the object's just going to fall straight down, which means that you don't have that normal force. But that's something, as you get into inclined planes, you'll discover on your own. The thing to remember, though, is the normal force is always going to be pointing perpendicular to that surface. So let's take a look at 3 different situations here, and we're only going to deal with flat surfaces. We're not going to deal with an incline right now. So here's the first situation, and it's exactly what I described previously, but now we're going to put some numbers to it, and we're going to think about it. So a 6-kilogram box is at rest on the floor. What's the normal force? There's a couple of things in here that are extremely important that I look at. I see that it's at rest. So if an object's at rest, that means that the acceleration, the net acceleration, is going to be 0. Well, if the net acceleration is 0, then if you think about it, F net is equal to ma net. If this guy right here is 0, then that means F net is also equal to 0. So that's kind of the key to this problem here, is that everything's at rest, which means we're not going to be moving, we're not accelerating in any way, so all of those forces should cancel. So this information right here tells me that the forces cancel. So I'm going to go ahead and give myself a quick free body diagram. So I don't have to worry about drawing an actual box. Free body diagram, also known as a force diagram, is just the object is just represented as a dot. Because I'm close to the surface of the earth, I've got weight acting on the object, and because I'm on the floor, I've got that normal force pushing up. So what I like to have my students do is I like to have them put it into a chart. You've got all the forces in the x direction, all the forces in the y direction. We have nothing in the x direction, so I don't have to worry about it. But in the y direction, I've got 2 forces. We're also going to look at just standard labeling conventions. So we'll call to the right is positive and up is positive, to the left is negative and down is negative. Officially, you can label those as whatever you want, but we'll just go ahead and keep it simple. So all the forces acting in the y direction. Well, I've got normal force acting up. So the normal force is positive because it's acting in the upwards direction. And then we've got weight, and that's acting downwards, so it's going to be a negative force. Because the F net is 0, and here's again the key, if I sum all of the forces in the y direction, they should end up equaling 0. So I'm going to go ahead and sum all those forces. I've got the positive normal force, and I've got the negative weight. So all of those together should equal 0. And if I'm ultimately looking for the normal force, then I'm going to go ahead and rearrange by adding W to both sides. And I find out that in this case, the normal force is equal to the weight. From previous little bits, you should remember that the weight of an object is equal to its mass times the acceleration due to gravity. And the acceleration due to gravity, we'll go ahead and say that that's equal to 9.8 meters per second squared. So let's go ahead and plug that in. We know that the normal force is now equal to the mass of the object times the acceleration due to gravity. We know the mass of the object is 6 kilograms. We know the acceleration due to gravity is 9.8 meters per second. So at this point, we're just plugging and chugging. 6 times 9.8, which will give us a normal force of, plug that in, 58.8 newtons. There we go, 58.8 newtons. So that means in order for this object to not fall through the table, that table has to give 58.8 newtons of force. If we add more mass to the object, then this mass will get bigger, and that'll have to supply a larger force. If we take away mass from the object, then the mass will get smaller, and that table has to supply less force to it. So again, it's kind of a lazy force, only does as much as it needs to do. So let's go ahead and take a look at an example where the normal force wouldn't equal the weight, because that's one thing that a lot of people get confused about. The normal force does not always equal the weight of the object. It's something that you have to figure out and decide for yourself. Normal force is going to be a little bit lazy. So here's an example. We've got a 6 kilogram box being pulled at a constant speed by a rope that makes a 30-degree angle above the horizontal. So all of that is kind of just telling you about the situation. What I like to do is I like to draw it all out. So if you can't imagine what's going on here, then you've got a box sitting on a surface, and there is a rope attached to it, pulling it in this direction, and that rope makes a 30-degree angle. It also tells us that the rope is supplying 35 newtons of force, so that means it is pulling with 35 newtons up and to the right. In this case, I decided that it was being pulled to the right. It doesn't specify one way or the other, so technically you could say that it's being pulled to the left. But since we read from left to right, a lot of people are more comfortable with objects moving to the right. So now that we've got our little picture gone, I'm going to give myself a free body diagram, because again, that is an excellent way to start off any force problem. We are close to Earth, so we're going to have some sort of weight acting on the object. This object is resting on the ground, so it's going to have a normal force. And I should mention at this point, I'm not going to worry about the lengths of these vectors. That's partially what we're solving for. Oh, it doesn't say on here, but we're going to calculate the normal force. So we're not worrying about the lengths of the vectors. Right now, we're just kind of getting an idea. We've got the situation, we're going to look at the physics behind it, and then we're going to plug in some numbers. In this case, we've got a tension force. Ooh, that's a little bit curved. A tension, because it's a rope. And I'm going to go ahead and give myself a little note saying that it's a 30-degree angle there. It says that it's being pulled at a constant speed. That's another one of those identifiers there. So if it's being pulled at a constant speed, that is, again, that the net acceleration will equal 0. Because the net acceleration equals 0, we know that the net force will end up equaling 0 as well. Well, if we look at this, we know that the net force isn't equal to 0. So we can actually assume that there is some type of force going this way to cancel out the rightward force of the tension. And we can probably determine that it's the kinetic friction. And we'll talk about friction in a little bit. And by a little bit, I mean the next video. But for now, just know that there is that kinetic friction. We end up not using it, but it's just there to keep us thinking about it. So now I've drawn my free body diagram. I'm going to go ahead and give myself a little chart. Split it off into the X and the Y. In the X direction, again, we'll go ahead and say standard convention. In the X direction, I've got the kinetic friction. The kinetic friction is pulling it to the left, so that's negative. And then I've got the tension, and that's pulling it to the right. But it's not all of the tension. It's just one component of it. It's the X component of it. Because you see how it pulls up and to the right? That's using those vector ideas. We've got different components here. Some of it is pulling it to the right, and some of it is pulling it up. In this case, we only care about that X component because we're writing the X chart. So let's look at the Y component. In this one, we have weight pulling it down, so it's negative. We've got the normal force pulling the object up, so it's positive. and we've got the tension force pulling it up or positive because it's up. And again, it's not all of tension, it's just that y component. In this case, we're solving for the normal force, so I ask myself which chart the normal force is in. I see it here in the y direction. So I'm going to go ahead and start figuring out the sum of all the forces in the y direction. If the net force is 0, then I know that the net y force has to be 0 as well. So I can say that the sum of all the forces in the y direction is 0. So I'll go ahead and put all of those y forces now. We've got the negative weight, we've got the positive normal force, we've got the positive tension in the y direction. All of that equals 0. If we rearrange to get the normal force by itself, we find out that the normal force is equal to the weight minus the y component of tension. On the previous problem, we reminded ourselves that the weight is equal to mass times the acceleration due to gravity. And if you think back to how you dealt with vectors, you can use some right triangle trig and determine that the tension in the y direction is equal to the full tension, the hypotenuse, times the sine of the angle given. So if we plug in some numbers here, and as we're going through this, we have to ask ourselves if this answer makes sense. So at the very end, we'll kind of talk about what I mean by that. But there's actually a way to determine if your answer is kind of on the right track or not. Oops, sorry, 30 degrees. So the normal force is equal to that 58.8 that we determined earlier. And if we plug this into our calculator, or if we think about our unit circle, we know that it is going to be sine of 30 is half, so 35 times 1/2 is 17.5. And last but not least, go ahead and simplify this. We find out it is 41.3 newtons. So what I meant by does this answer make sense? The normal force, again, is a little bit lazy. So if we look at our diagram, we can actually see that the tension is pulling up on it. Well, if the tension is pulling up, that means that the normal force has to pull or push less. So in the previous problem, we found out that the normal force was 58.8 newtons. Well, it makes sense that this normal force is less because tension is helping to make it so that the normal force can do less, push less on it. So anytime you've got something assisting the normal force, that normal force should be less than if that force didn't exist. So yes, the normal force when the object was just kind of lying there, so from the first problem, is less than the normal force from the second problem, because in the second problem, tension is helping out there. Let's go ahead and take a look at one more type of problem here. And the last type of problem we're going to be looking at is instead there's somebody's pushing down at an angle. So take a minute to read that. And what I would actually encourage you at this point is you have enough information to solve this on your own. I would strongly suggest taking a moment, seeing if you can figure it out, pausing the video. If you get stuck, then hit play and then get to the point where you can figure it out and then say, oh, okay, let me pause it again and start it. So hopefully you went ahead and tried that, but I'm going to go ahead and draw a picture of what's going on here. Here is the box. Now we've got somebody pushing the box, and they're pushing down at a 30-degree angle. So they're actually pushing down like that with a 30-degree angle there. So as I'm drawing this free body diagram, we are close to the Earth, so we've got weight. It is resting on a surface, so we have a normal force. And we always make sure that the tail of the vector is on the dot. So even though it's pushing on the corner of the box, we're going to go ahead and move that vector until it's coming from the free body diagram there. So here is the force of the person. We'll go ahead and say that. Force of the person. And again, it says that it's moving at a constant speed. So we can again assume that there is a frictional force here. So because it says a constant speed, we can say that the net acceleration is 0. Because the net acceleration is 0, the net force has to also be 0. So here's my x and my y chart. Standard convention, positive, positive, negative, negative. In the x direction, we've got the force of friction, which is keeping it going to the left so it's negative. We've got the force of the push or force of the person that's going to the right, but it's not all of that force, it's just the x component. In the y direction, we have a positive normal force because it's going up. We've got a negative weight because it's going down, and we've got the negative person, specifically just the y component. Again, because the net force is 0, that means the components, Fy, also has to be 0. So the sum of all those y forces, here's your normal force minus the weight minus the force of the person in the y direction. All that has to be 0. Some algebra brings us to the weight plus the force of the person in the y direction. Then we have from the previous section, or from the previous number 1, we reminded ourselves that the weight is m times g. And again, using right triangle trig, so we've got the x component there, we've got the y component there. The hypotenuse is Fp, which we're told, so we can say the hypotenuse times the sine of the angle given. Using SOHCAHTOA, we know that the sine is equal to the opposite over the hypotenuse. Rearranging, we get this. So plug in some numbers. The normal force is equal to the 6 kilogram box times the acceleration due to gravity, plus the force that the person applies, 35 newtons, times the sine of the angle given. And again, now it's just plugging it all into the calculator. Normal force is equal to 58.8 plus, this time, 17.5. And now that gives us our final normal force of 76.3, which again, this answer does make sense because now the person pushing is pushing down. So they're pushing to bring the box further into the surface, I guess the floor, which means the normal force has to push harder to make sure that it doesn't go through the floor. So our answers had that the smallest normal force was the second case because the rope was helping to alleviate some of that necessary. And then the first situation was the next biggest because it was just the box on the floor by himself. And then the very last situation, the third situation, had the highest normal force because in this case somebody else was pushing down on it. So again, normal force, quick review of it, it's a supportive force. It's a little bit lazy in that it only pushes as hard as it needs to. And the fact that it's called normal force is because it's always perpendicular to a surface. In all of these examples, that normal force pushed perpendicular to the surface, which in this case was the ground. So make sure you guys keep those in mind as you're working any sort of problem that talks about normal force.